Hello, everybody. All right, so let's keep talking about magnetic fields. In our last lesson, we learned about how wires produce magnetic fields. Right, we looked at Oersted's law, which was the concept of moving charges producing magnetic fields at right angles to that motion in a loop, in circles. Right, and we developed something called the right-hand rule that allowed us to figure out the way it loops around. Right, so just quickly remember orienting myself there. There's the current, and then our fingers close in the direction around it to produce our magnetic field. Now we also saw, again, I apologize. The audio did mess up in that video that we watched, that old video, the old lab video. If you go back to lesson 4 in the description of the video, I posted that actual video with the audio correct. I'm sorry about that. I don't know what happened there. That was weird. However, we did see that for us to actually generate strong enough magnetic fields in these wires, it requires a ridiculous amount of current in the order of magnitude of thousands of amps. So we can't actually produce very strong electromagnets from just single wires. We need to find a way that we can produce electromagnets in a more efficient way instead of just a wire. One wire will not produce enough magnetic flux to be useful. So since it's so low, why don't we put a whole bunch of wires together in some way that is efficient? And the way that we can do that is called a solenoid. And that's just a coiled up loop of wire like this. So in this picture, you can see we can have some current going in. Let's say the current's going up in this way. It's going to go up around here, and then it's going to keep going around and around and around and around. And each of these wires is going to generate a small magnetic field. But then when we add them all up, we're going to actually get a much larger magnetic field heading this way through our coil. Let's look at this a little bit closer. So let's consider just one piece of the coil, just one loop. Okay, so let's just so this is this one loop, and the current, let's say, is going down through it like this. Okay, so the current is heading down through the wire. Now, using our right-hand rule, we can show that in this case, remember this dot, where is it? There it is. This dot means that it's coming out of the screen. So it's going to be coming out of the screen. And our fingers are going to close around like this. So this will be, what's that? That's counterclockwise. Alternatively, once the current heads down the wire, this picture here, this is a cross section. So this circle here represents that circle there. And this circle of the wire of the current going in is this is this circle here. Okay, so we imagine in the picture in the middle here, we're looking at this image here, these field lines, just on a two-dimensional plane. And now if we do the same thing, this is now going into the screen. The magnetic field is going clockwise. So, and as you can see, the magnetic fields on the inside, since these are all heading this way, and these are all heading this way, we add up. So each time we add another loop and another loop and another loop, we add a little bit more and a little bit more and a little bit more. And you can coil these as many times as you want, right? And you can come up with quite strong magnetic fields. Okay, so when we put these together, we end up with this magnetic field going through. There's a magnetic flux. Flux just means flow. Flux is a fancy pants word for a flow of a magnetic field. Okay, and for us to figure out the direction of it, we have another right-hand rule. Again, we're going to use our right hand. And as you can see, this is why we never change the conventional current. We have all these rules that are developed around them that would have to be changed. So we keep we keep using that. The current in this case, let's look at this example here. So the current is heading up this wire, so it's going up on the outside, and then on the back side of the coil, it's going down. So these are all up, right? So all the coils, the current is going up. So we're gonna we switch. So previously it was the magnetic field lines were our fingers and the current was our thumb. Now for a solenoid, we just do the reverse. Sorry. So the fingers are going to represent the current. So my fingers here, whoop, this way, my fingers are going to represent the current going around. I'm going to close my fist around the solenoid, and my thumb is going to point in the direction of the magnetic field, in the direction of north. Okay, so you can see here that the fingers are going over. Oh, my camera is backwards. It won't work this way. So the fingers are going over, and the thumb is then in the direction of north. So remember that. So solenoids, it's backwards. So with a wire, the thumb is the current and the fingers the magnetic field. With a solenoid, the fingers are the current and the thumb is the magnetic field. But we always use our right hand. There's a right hand rule for wires and a right hand rule for solenoids. So fingers go around the solenoid and our thumb points in the direction of north. Okay? And for the strength of it, it's going to depend on the number of turns, which is n here, the number of times you go around, and it's also going to depend on how much current we put through. It's going to be proportional to the number of times I go around. Right? Every time I double the number of loops, I'm going to double the strength, right? Because they're going to just keep adding on to each other. It's linear. And every time I increase the current, I'm also going to increase the magnetic field. It's a linear relationship there. However, if I stretch out the coil, if I make it longer, it's going to go down. So really, I'm looking at this N over L here. This represents the turns per meter. So it's like a density of turns. The tighter you can coil them up, the more magnetic field. Like for example, in an electric guitar, the pickup is made up of one of these solenoids. And they use incredibly fine copper wire, a very, very, very low gauge copper wire, and they wrap it around thousands and thousands and thousands of times. So inside an electric pickup, even though the pickup, it's a small little box or a little thing, the number of turns in there is in the thousands. Because the higher density, right, when you have a very, very thin wire, you can get a very high density of turns per meter, and you can get a magnetic field. In that case, an electric pickup is sort of the opposite of an electromagnet. It moves a magnet within a coil and it produces a current, as opposed to a current producing magnetic field. But don't worry about it. That's induction. We can talk about that later. Especially if you're going to make we have to make a. You guys can make one yourself. You can make an electric pickup. All you need is a magnet. If you're going to make an electric guitar we'll talk about that later, but if you want to make an electric guitar, well, you did that last unit. What am I talking about? That's unit 4. Okay. So, yeah, I'll stop talking. Anyways, now the constant is what we call the permeability constant. It's sort of a measurement of how easily magnetic fields can travel through a material. If there's nothing in the core, what I mean by core, I mean the space in between the coil. Like for example here, there's just air. If there's nothing in there, then it's the permeability of free space, which we call mu naught. This is a physical constant of the universe. It's how well magnetic fields travel through a vacuum. And it's equal to 4 pi times 10 to the negative 7 Tesla meters per amp. Oh, I should probably talk about this. The unit of magnetic field is Teslas. Okay, not the car, named after Nikola Tesla. And it's either, you can think of it as kilograms per second squared amps or kilograms per coulomb second. You don't have to worry about that. Just know that the units that we're going to measure magnetic field is Teslas. And the permeability constant is 4 pi times 10 to the negative 7 Tesla meters per amp. Right, Tesla meters per amp. Because we're going to cancel out the meters from the length, and we're going to cancel out the amps from the current here. Now you can change this mu, like if you, for example, if you put an iron core within an electromagnet, within that solenoid, it's much easier for the magnetic field to travel through that ferromagnetic material. Iron, we call a ferromagnetic material. The magnetic domains inside it are very easy to manipulate. Uh, they're they're magnets. Ferro means iron. Um, they have very good magnetic properties. So if you put an iron core within a coil, the permeability here is much higher. Right? This 10 to the -7 tells us that um, really it's very difficult to make a strong electromagnetic with no core. You can increase this much higher with something like iron, and that's why electromagnets always have some sort of core inside them. As you can see, this number is quite small. So let's actually do an example to see what sort of numbers we can get, what sort of magnetic fields we can get with a air-cored magnetic field. Air-cored solenoid. So let's say we have a coil of wire, 2,000 turns, 2.0 times 10 to the 3 turns. We've done that over a space of 50 centimeters, and we're going to put 15 amps of current. 15 amps is quite a lot. It's the amount of current that comes out of a wall plug. Okay, so this is quite a bit of current, quite a lot of turns. 50 centimeters, that's a decent size. So what kind of magnetic field will this generate? So we're going to take our formula that B, the magnetic field, is equal to mu Ni over L. Substituting in all of our values, 4 pi times 10 to the 7 Tesla meters per amp multiplies by 2,000 turns. Notice that 2,000 doesn't have any units. Times 15 amps divided by 0.05 meters. Oh, excuse me. That's a little mistake there. That should be 0.5 meters. Okay. Sorry about that. All right, so we have 0.5 meters, which is 50 centimeters, and we end up with a magnetic field value of 0.075 teslas. So as you can see, that's be 57 milliteslas. It's quite weak. So really though, that is quite a strong magnetic field. When we talk about teslas, Tesla is a big magnetic field value. Let's see, for example, everybody okay with this? Yeah, okay, so 0.75 teslas. We just plug in the numbers and we're good to go. What does that mean? Here, I'll give you a sense of this. The Earth is only, what would that be? That's 32 microteslas. Okay, so the magnetic field required to point a compass is only 32 microteslas. This list I just copy and pasted from Wikipedia. Your typical fridge magnet is 5 milliteslas. Your neodymium magnets, so the much stronger ones, the silver magnets that you can play with that are very strong magnets, difficult to separate, they're only in the order of like 1 Tesla. If you ever have an NMR, magnetic resonance imaging, MRI, or nuclear magnetic resonance, if you ever go to a hospital and they put you in a massive electromagnet, that has the power of, again, 1.5 to 3 Teslas. Okay, so this is a very, you've seen, well, maybe not, maybe watch some scary videos of people with forgetting to take the chair out of an NMR room or something like that, and how strong that really is. What else we hear? The maximum, the world record for a magnetic field is 45 Teslas. So that's an incredibly large number. Theoretically speaking, there's something called a magnastar, which is a neutron star that produces magnetic fields in the gigatesla range that would do some very strange things to everything. Basically, atoms can't form. Atoms can form. Chemistry can't happen. Molecules can't form because the electron orbitals kind of would become these filaments. We get squeezed out into these incredibly long, thin things aligned to the magnetic field. Basically, nothing would work properly. Nothing. Chemistry could not function just due to the fact that electron clouds in an atom are no longer the electron clouds we would expect them to be. It would do some very strange things. One last thing I want to talk about here. Apparently, if you put 16 Teslas on a frog, the tissue, the water in the tissue, will actually uh, become magnetized, and you can actually levitate a frog. The 2000 Ig Nobel Prize. Ever heard of the Ig Nobel Prizes? It's like the Nobel Prizes, but the funny version of the Nobel Prizes. They actually, in the year 2000, they awarded the Ig Nobel Prize to a team that was able to show that 16 Teslas of magnetic field will levitate a frog. All right. There we go. There's something we can put in our textbooks. All right, so just for homework, these 4 problems, draw some pictures, calculate some field strengths, and we can go from there. All right, so solenoids, basically just a coil of wire that generates a stronger magnetic field by adding our things. And right-hand rule for solenoid, remember we close our hand in the direction of the current and the thumb points north. All right, okay, so I hope you guys are all doing well, and we'll be talking to you later. Take care.